This meeting is being recorded.
Welcome everyone to the seventh talk of the Stefanich-Tannaka seminar. So today we have Robin from Osnabrück, and Robin's going to be talking about the admissibility of QCoh CN, that is the connected objects in the category of quasi-coherent shapes of X. So please, Robin, take it away.
All right. Hello, everybody. I'm happy to be here and happy to organize this seminar with you, Amatya. So today we are going to see the first talk where we are moving towards somehow our main goal of Tannaka duality. So today is going to be about admissibility of QCoh CN. And so first of all, because we are somehow, the setup was meant to be slightly different. So if you can't read anything for any reason or you have any question, please don't hesitate to ask. Okay, so let me maybe, because we're somehow, there's somewhat of a break in topic. So let me say a few introductory words maybe on what we're actually doing now. So somehow, the main technical ingredient in Tannaka duality, or at least in the Stefanich version of Tannaka duality, is
Robin, sorry to interrupt. Could you please write a bit bigger?
I can try, yes. Is this better?
Yes, that's good. Thanks.
Yes. So yeah, it's bad if you're both small, if the writing is both small and bad. So thanks for pointing that out. Okay, so the main technical ingredient is somehow some affineness result. So how does the story classically go? So we start with X in affine scheme, and then we can consider this global sections functor, which starts at quasi-coherent sheaves over X, and it goes to modules in the sections of the structure sheaf in abelian groups. And this thing is an equivalence, which somehow characterizes, it even characterizes these affine schemes, right? So this is really an equivalence. But okay, so this somehow gives us some control over what these quasi-coherent sheaves are. And now, for us, there will be a similar result, which is some categorified version of this. So you can categorify this, and then you start with X and nice enough, let's say. Stack. And then, once again, there exists some global sections functor, but now this thing has some cryptic markings, NH and com. This stands for complete, this for enhanced. And this goes from some 2 category of quasi-coherent sheaves on X. 2, and now somehow there's a version of the right side, so it's again a module category. But now over QCoh X connected in Okay. Yes. So and this is an equivalence. So this is somehow the result that we're now working towards. And okay, right now you don't really know what this is or what this is possibly, and we don't know how the equivalence works. But today we are going to talk about the right side, and then next time we're going to talk about the left side, and the talk after we will see this equivalence. And then using this, one can then show Tannaka. Okay. Maybe as an indication, on the right side, as long as you believe that this is really some algebra object, maybe it's believable what this is. On this left side, this is a subcategory of the limit of mod modules over mod RC connective in Rot over spec R2. So, I mean, this is somehow some category of some categorified version of quasi-coherent sheaves on R, and now somehow you approximate by these things where you can actually say what you want, and then you take a look. Yeah. Okay. Right. So today we will worry about the right side only. So
Robin,
yes.
sorry to interrupt. So don't you mean that like this category, this is like a full subcategory that consists of the sheaves whose values is like a complete coordinate pre-stable category?
Yeah,
The comp?
say that, yes.
Oh, okay,
Yeah, I
okay.
agree.
Okay.
Right. So it's those where somehow at every like point wise you actually not only get any module, but you get a module which is already complete.
Okay, thanks.
No, you're right. But like I was just sort of giving some sort of rough idea what this is. But you're of course right. Yes. So okay. So this time this is an admissible algebra in yes. So if we have this, we can use all of the tools that we developed last time about admissible algebras and rigid algebras and such to treat this. So that's somehow one of the main points of why we did all. Okay, so let me write down the exact statement. Theorem A. So we start with QC geometric stack such that the diagonal is a QCQS relative algebraic space. And so, yeah, I mean, there's several, of course, several different conditions that you can have on the diagonal to be sort of a more nice kind of stack. But this is, I think, quite a lax condition. So then, if we have such a thing, then this here is an admissible algebra. I.e., what did this mean? This means that QCoh X and the connected part are a rigid algebra in Rot-Comp state. Yeah, so this was the definition of this admissibility. Okay. And if moreover, if delta x is affine, which is quite a lot more restrictive, then this is a rigid algebra. In Rot-Comp itself. So when we remember, I mean, the difference between these two things is somehow about this right t exactness of the sorry, again, I'm always confused with right and left. This yes, right is correct. The right t exactness of the right adjoint that you obtain. We will see that in a second again. So yes. So to prove this theorem, I'm going to state a different theorem, and then we're going to prove it, and then we will, in some time, get to the other proof. But first of all, let us note that if we have two such geometric stacks, then, so first of all, this thing here, this is a Grothendieck. This is a Grothendieck pre-stable category. This is really just due to it being the connective part of the T structure on all quasi-coherent sheaves. Okay, so that's the first part. And I mean, okay, then you have to also, this gives you pre-stable, and then you have to check that the truncation functor really does what you want. The connective cover functor really does what you want and commutes with filtered coordinates. Okay. And then secondly, it's complete. And this is really due to modules being complete, and then somehow some bootstrap argument. This is an HA somewhere. Oh, it's an SHA. So this is AG2254. Okay. So really, it lies in this category that we are concerned with, which is good. And we can consider the multiplication, which is simply given by first pulling back to the product and then multiplying. Okay, so let us call this something, maybe E of xy. So we're not really interested in this thing per se, because we're completed, so we should take all the completed tensor products. But of course, we can take the completion here. And so this gives us some completed version, because this is complete. So this really factors. And then the statement is very simply that if you take X such a geometric stack as we had before, so QC and delta X QCQS relative algebraic space. Then for any geometric stack Y, this completed multiplication EXY hat is an equivalence. Okay, so there's some sort of tensor product. You might want to call it Künne, but maybe not. So there's some sort of tensor product formula for these for this functor going on. And so now let us first deduce this theorem from. Right. So okay, so let X be a stack as in the theorem. And now let me recall, or let me maybe unravel these definitions on what we actually have to do. So what is to show? So we have this multiplication map EX, so E hat XX, which is really the multiplication of this algebra object. And then we can consider this as an object from, so as a map inside of this root const category. So as this pair, I'm gonna write it beneath each other because otherwise I don't have any. Okay, so we have this this thing, which goes from here to just the one where you've multiplied. Okay, and so this is the actual action map of the algebra object that we're interested in. So we want to see that this thing here admits a right adjoint. Okay, so that is was the first part of being a rigid algebra. And equivalently, if you remember how these functors were defined somehow, I mean, these are given, this category consists of, you have objects, a stable category, together with a Grothendieck pre-stable category, which gives you the stabilization. So the functors were given by functors of the stable categories, which were co-limit preserving and right T exact up to shift. And so somehow that exactly gives you what's happening here. So the underlying map in in here stable has a right adjoint and this right adjoint then has to give you a map again. So this has to be full-limit preserving and right. I'm always confused with right and left. I think right is correct. Yes, right T exact up to shift. Yes. Okay. And then the second condition is similar. So the second condition was that the associativity square in holds com is right adjointable. So here it really doesn't matter. I mean, it should be horizontally and both horizontally and vertically. And this is equivalent to the underlying associativity square in PR stable being right adjointable and the right adjoints are co-limit preserving and right T exact up to shift. Okay, so, and I mean, this right adjointability is somehow okay because all of these functors are co-limit preserving, so it's really about this condition of the right adjoint. Okay. And now we use Wieser theorem to identify what these maps are. Okay. So, right. So this theorem identifies the tensor product with the with quasi-coherent sheaves on the product. Theorem B. We obtain a commutative triangle. This looks like such. So we just consider this isomorphism from the theorem. And okay, now there are two ways of mapping into QCoh X here. One is exactly this multiplication map. Oh no. Yes. So this is this map on mu x, mu x, let's say. And the other one is pullback by a delta. Yes. And so this equivalence up here identifies this map that we're interested in with pullback by a delta. And so now we can somehow answer all these questions by just using properties of the pullback. Okay. Thus, if you apply an X vector to this, with the pullback along delta on QCoh instead of QCoh connected. Okay. And the associativity square so this identifies with QCoh of the following thing. We take this triple product, and then we can take identity times diagonal, and we can take diagonal times identity to it, and then we can take the diagonal. Yes. So this square after applying QCoh exactly gives us this associativity. And note that this is Cartesian. And now that we have these facts, we can just apply some more or less basic results on quasi-coherent sheaves by Lurie, which immediately give us what we want. So now use SAG 3422 and 3423 to compute. And so what do these things say? F from x to y, a relative algebraic QCQS, relative algebraic space. So this is exactly delta of x in our situation. Then we have the following. So F upper star admits upper star on QCoh. Admits a right adjoint. F lower star. So that's already good. So we have our right adjoint, and now we have to just check that this thing here is column preserving and right exact, and that's what the proposition says. Right exact up to a shift. I didn't say that earlier. Up to a shift. Okay, so this is the first thing, and then the second thing. secondly, if f is affine, the push-forward functor is correct. Okay. And secondly, for this diagram, what we do is that if you take any such Cartesian square, of QCoh as relative algebraic spaces, then QCoh of that square of the square is right adjoint. Yes. So, I mean, this first part gives us exactly the first property, and the second part gives us the second property. And you might wonder, why did I say this? We had this extra condition, or this stronger statement, that if f is additionally if x has affine diagonal, then we don't get this inside of this category where we have right t exactness up to a shift, but actually inside of Qoh itself. And because this is right t exact, it induces a functor on QCoh connective. So we have a right adjoint on QCoh connective, and this is right t exact, and Coulomb preserving, and then you can just run this entire thing again, but now not with QCoh stable, but with QCoh with Qoh stable, but with Qoh. Okay. Other questions so far? No. Okay. Then we will talk a bit about how the theorem works. Ah, no, I have more thoughts. Okay, so that concludes this proof, and so what is the strategy for theorem B? So we start with some general stack X, which might be somehow not so easy to understand, but maybe if X were affine, this would be easier. So maybe we can use some sort of descent statement, as one often does, right? So maybe we take U to X, a faithfully flat map with U affine, and then we can consider the Chekhov. And this thing resolves X. And so now we might be interested in using this somehow. So if we consider the map that we're interested in, we can map this here into, just by mapping this left side, somehow into any of these components of this Chekhov. And then we can totalize this thing. So we take the limit of this, and then this gives us a map. So basically, I mean, this is now a co-simplicial object. This is somehow some augmentation of this, and you take the totalization. And similarly here on the right side. But this is now somewhat nicer because there's no like tensor property. And here's also a map by just taking all the totalizations of the maps on the inside. Okay, And so somehow, what can we say about this diagram? This thing here on the right, so u times, if you just take the product with y, this still gives you the faithfully flat map. So this thing here is an equivalence. And similarly, maybe we've taken, so if the theorem holds for x equals to un, then this is an equivalence as well. And so we only have to show that this is an equivalence on the left, which is exactly some sort of descent statement. So that's the idea to show this.
By the time you're erasing, like there's a comment, like one comment. Could you maybe try not to write on the extreme right of the board? I mean, it's a bit blurry. What's the extreme right?
I will try.
Okay. Maybe you could draw a line, like a few inches.
So where is it still okay? Like what here?
A bit to the right.
Like here?
Yeah, it's almost okay till that point. Yeah.
Okay.
Thanks.
Thank you. Okay. All right. So now, oh, that's the wrong thing. Okay. So now we want to show this descent statement, and there's a very general sort of principle for this, which involves something called monadicity, or in this case, comonadicity. So let me try to explain this. So, and this is somehow a very nuts and bolts definition now. So we define categories delta and delta plus and delta minus infinity as follows. So delta plus is the left cone of delta. So you add one additional element, which is initial, and there's no morphisms into it which aren't the identity. So you should think of maps out of this as cosimplicial objects, and maps out of this as somehow ones where there's an extra element where there's an extra object at the start. And okay, this thing here has the same objects as delta plus. I mean, okay, we call this thing n for n minus 1, and this minus 1 is this extra thing that you get in delta plus. But the mapping space between two of these is now slightly different. It's a bit larger, so you have order-preserving maps. N, but now you join one extra point. Nuri says minus infinity, but maybe you just want to call this minus 1. I'm not quite sure. Like so, such that minus infinity goes to minus infinity. Okay, so it's this thing. This is more for completeness than for what happens. But if you are familiar with somehow split equalizers, and you look at this long enough, then this might sound familiar to you. Because if you somehow truncate this at stage 1, you get exactly the split equalizer diagram. map out of this. So, and because of this, so let this be a functor, okay. These are called augmented cosimplicial objects. X is split. If it factors over delta minus infinity. And so again, if you cut all of these things off at stage 1, then you get exactly like forks and split co-equalizers. Sorry, split equalizers. Yes. Okay. And if f from C to D is a functor, x is called f split if f composed with x is split. Yeah. So if it becomes split after mapping along f. And so why are these things interesting? The answer is, or one of the answers is, the following lemma, which is HTT 6.1.3.16. So you start with some split cosimplicial object. Then there's a map from x minus 1 into the limit of x restricted to somehow the part that's not this one object. And this is an equivalence. So somehow just being split, I mean, just factoring through this category gives you that it's already a limit, which is pretty strong. In particular, because does any functor f from C to D preserves such limits? Because any functor preserves split objects, and if every split object is such a limit, then somehow. Also, maybe notation-wise, I mean, here I said limit over this thing. There I said totalization. This is of course the totalization, right? Yeah. Okay, so this is already somehow helpful. But the really helpful thing is the following. So let me define something first. So we start with some functor. This functor is called comonadic if three things are true. F admits a right adjoint. Secondly, F is conservative. And thirdly, and now here come the split objects. F let X from this augmented category to C be an F split cosimplicial object. Then X has a limit in C, and this limit is preserved by F. Okay. And somehow this definition, or what you can do with this definition, is the reason why I introduced these split objects. I don't know whether you've seen monads or comonads before, but basically it's some sort of algebraic thing that encodes an algebraic structure, or something I would think of as an algebraic structure on a category. And you can take modules over it, and basically this F here is comonadic if and only if it's a forgetful functor from a category of comodules over a comonad. So this is how you should think of these. And maybe the classic example, not for comonads but for monads, is somehow the free forgetful adjunction, which gives you a free module, and then the right adjoint is then monadic, and this left adjoint that you get here, because it's of course op.
So this F composed the right adjoint will be a monad, or will be a comonad in D, right?
F composed the right adjoint. Yeah, or the right.
Sounds correct.
One or the other is a comonad. This gives you a comonad in
D, I think.
So comonads have co-units. So the co-unit should go from the comonad to the unit, and so the comonad should be the left adjoint and then the right adjoint. So it's F composed with the right adjoint. So I think you get a comonad over C.
Ah, okay.
Yes. Yes, and I mean, wait. No, that doesn't make sense.
No, it should be over D, I think.
No, I mean, it should be over D, yes, because like in the end, this thing should be some forgetful functor from, and this should be the category of comodules over this.
Right, right.
Yes. Doing right and left is really hard when you're at the board.
True. Thanks.
Yes. So you get a comonad over D, and this this induces then an equivalence between C and this category of comodules. Okay, so but now somehow we don't need it for that. We need it for this next thing, which connects comonadic or monadic functors with descent. So this is HA4753. So we start with C to cut an augmented co-simplicial category. Oh, I did the thing wrong. Yes, I was actually not right there. Okay. And so we're interested in the criterion when this is already, when C minus 1 is already the limit of this, or the totalization of this, of the rest of the diagram. And it's going to be the following two conditions: F is comonadic, and for F, I didn't say what F is. So you start, you take the functor which goes from this minus from this object that we want to be the totalization to the first object in the resolution. This thing should be comonadic. And for every alpha from n to n, we have a diagram which looks like this. Here you take alpha, and here you take somehow d0, which is the zeroth degeneracy. This is vertically right adjoint. Okay, and if you have these two things, then this is an equivalence. Okay. And so this was somehow of a digression, but if you look at this, now it might become obvious that somehow we have exactly such an augmented cosimplicial object, and we want to check whether this thing is an equivalence. So we need to apply this criteria. And there's two parts now. So let's do them. So any other questions maybe?
So it's like, I don't know, it's not exactly a question, but so there's decent data for a cover. It like corresponds to co-algebras for the associated monad, comonad, right?
I'm sorry, can you say again?
So I'm saying like this. So the decent data for a cover that corresponds to co-algebras for the associated comonad,
Yes.
right?
I mean,
Yeah.
or monad. I mean, you can
Yeah.
if you have like the opposite condition here, that these are left adjointable, then of course you want your functor to be monadic.
Right.
So either one works really, but somehow the descent data using this can somehow be thought of as some like algebraic information.
Yeah. Thanks.
Okay, right. Okay, so this first step that we want to have is that I need to properly state what we're doing. Okay, so the thing that we're now working towards is the following. QC geometric stack such that delta x is a QCQS relative algebraic space, and P from U to X a faithfully flat map with U affine. Then for any we're complete. I think this should say complete. For any complete coordinate pre-stable category, we can consider this tensor product and map it to the totalization. Okay, then the equivalence. Okay, so step one. So we start with this map, which is our functor f in the theorem. And we want to show that this is comonadic. right. So let's first note that this functor, which is just, I mean, it's just pulled back along this map. This is left exact because it's flat, and conservative because it's because it's faithful, right? Faithfully flat things induce left exact conservative. Okay, so let's start with the lemma, which tells us that these things are exactly comonetic. So a functor between complete Grothendieck free-stable categories if F is left exact and conservative, then is comonetic. Okay, and if we remember briefly what being comonetic means, we want to have a of course this should be colimit preserving. Yeah, I mean all our functors preserve colimits, right? So yeah, should be colimit preserving. Okay, so because it's colimit preserving, we have a right adjoint. Then because F is conservative, it's conservative. And so the only thing that we have to check is that if we have an F split object, then the limit is preserved. Okay. So let X be an F split cosimplicial object. Okay, and we need to show that F preserves the totalization. Oh, I mean, really of X restricted to delta, but okay. Right. So D is complete. So it is enough to show this after truncating. But now, because F is left, the truncation, F and then the truncation is the same as first the truncation and then F. And now this F here is the F after applying truncations. But if you restrict it to here, this preserves totalizations. As these two are n+1 categories.
Robin, is it F compose tau or tau compose F?
Yeah, they're the same.
Oh yeah, of course.
So here I said somehow it's enough to, so we want to check that F preserves it, but somehow applying all of the taus is conservative. So it's enough to check it out. But then it's the same because F is legs.
Thanks.
Yes. Okay, but now these two are n+1 categories. So, and this is a left exact functor. Yes. And so this statement actually I didn't find a good reference for it. but I convinced myself that it's true enough somehow. But I don't think I have time to somehow present it. But basically, the idea is if you have a one category, if you have like an n category, then restriction to somehow the first n plus one parts of delta, and including this into the whole of delta is and now I'm never sure. It's cofinal, I think.
N minus one or
Two words, right? So
n plus one or n minus one?
The first n plus one things, and then it's a finite limit. So then lex being lex is good.
Yeah, I was just wondering if it's n plus one or n minus one.
It should be n plus one because you need to do the first two if you're one category, I think.
So you said in an n category. You said you're starting off with an n category, right?
Yes.
And then, okay. Sorry. Yeah, sorry.
I think first n plus one elements of the
Yeah.
to the whole thing after mapping to our n category is cofinal, I think.
Right. Thanks.
But like, I mean, so here you need to take at first n plus two things, but it's really the index doesn't matter, right? You just need some sort of finite limit, so we can apply the index.
Right.
Thank you. Okay, thus enough. The truncation preserves the totalization of x. All right. And so now we've used completeness of D, now we use completeness of C. Since C is complete, it's enough that this truncation preserves the totalization of the n plus first truncated part of x. And here I think this is some inductive argument, because you can somehow you can build things. I mean, you can somehow like build this inductively up by both making this and this n bigger. So it's really enough to check it only for the next one. But yeah, I mean, I don't actually think this also matters here. I think you could also just take any n here. Okay. But then f is conservative. This is equivalent to f composed with this truncation, which is the same as the truncation composed with f, preserving the totalization. And now again, f restricted to n plus one truncated things, preserves totalizations. So we need to check that this truncation preserves the totalization of f applied to this truncation. But now again, f commutes with the truncation. But now we've started with something with a simplicial object and have applied f before taking the totalization. So now f of x is split, so all functors preserve the totalization. in particular, both this truncation and this truncation. Okay. Okay. Other questions about those? Okay. So if we check, let me before I actually I'm going to change the words. So let us consider for a moment. Let us consider this thing. So right now we somehow know something about this map without the tensor products. So the thing that we're interested in. Oh, wait a second. This should read. Sorry, the spectrum missing here. This should read. Like so. Because we need to. Yes. Okay. I think you want this for the spectra, but it's also arguably true before the spectra, but we want it for the one with the spectra. Okay, so right now we know it for this map without the tensor product and without the spectra. So next, let us consider first the tensor product and then what happens with spectra.
Right, so the map is like as P applied to P upper star, that's really the identity. Okay,
Yes.
I see.
I mean, it's P tensor the identity, P upper star tensor the identity, and then you take the spectrum.
Right, okay.
Right, yes. And leave my chalk everywhere. All right. So first tensor products. So F from C to D, coordinate preserving functor between complete coordinate decreasable categories. If F is compact, lax, and comonadic, compact, lax, and conservative. Yes. Which, as we've seen, somehow lax and conservative give you comonadic. And for every complete coordinate pre-stable category E, we have that the completed tensor product with the identity from C tensor E to D tensor E is lax and conservative. Okay, and so for this we need one other lemma which I don't want to show. This one I'm going to, but this other lemma it's not all that interesting, I think. So we take two coordinate pre-stable categories, and H from spectra over C to spectra over D, a left T-exact functor. We also call them in for something, right? Oh, yeah. Note that this is explicitly not induced by a functor between C and T. So yeah, it's just some functor on the spectrum. Then for E Grundig pre-stable H tensor the identity from SP spectra on C tensor spectra on E to spectra on D tensor spectra on E is left T exact. Yes. So if we somehow replace all of these by left exactness and we remove all of the spectra, then we had already seen this, and I think the proof of this is simple. So it's like a slightly different context. Okay, let us show the first lemma. So Flex implies by the lemma that we had earlier that F tensor the identity is Lex, which implies that the completion is Lex. Okay, so that's easy. And then for F tensor identity conservative, it is once again enough that for M0 truncated, with F tensor the identity of M equals 0, that we then already have M equals 0. Yeah. And the reason for this is once again completeness. So you can complete, and this is X. So if you start with somehow with an n truncated object, you can somehow resolve it by one which is further truncated and a zero truncated object, and then you use this. So you get inductively from zero truncated objects, you get this statement for all n truncated objects, and then because it's Lex, this commutes with the truncation. So this then tells you that all truncations of your object, if you take any object, then all truncations of your object are 0 if it's sent to 0. So then the object itself is 0. Yeah. All right. So, but completion is an equivalence on zero truncated objects. So we can show this for F tensor of identity instead. Yeah, so we don't need to complete. And so now let us consider the following diagram. Okay, this top is the method we're interested in. The bottom is the actually the bottom is the stabilization of the top, because I mean taking spectra is monoidal. So okay, so we can take a right adjoint to the spectron F because it's again Coulomb preserving. Say with unit theta from the identity to G SPF. And then we can take the cofiber of this. And we call it H. This is again somehow an endofunctor of spectral C. And now we take an M which has the property that it's sent to 0. And so we can consider the cofiber sequence from here. Like so. And because, I mean, this diagram commutes, so we've just included M in here and then applied this, but that's the same as first applying F tensor the identity and then including the spectra, so this is 0. Okay, thus, H tensor the identity of M is the suspended of M. And now we are going to use this result to get a together with the truncatedness to arrive at the fact that I'm okay. Right. So if H was left exact, then so would be H tensor the identity, and this is by the lemma. And here you have to be a bit careful because somehow you need that H actually preserves colimits, which isn't quite clear because somehow the SPF certainly preserves colimits and taking this cofiber too, but somehow G doesn't have to. But luckily we assume that F is compact, which actually gives us a G really preserves colimits. So this is why you can apply the lemma. But then sigma of M is 0 truncated. And then M is 0. Right. So the only thing that we really have to show is that H is left. So we can this is a slight reduction. We start with something which is in the heart. It's a very ugly heart. For every we have that the core fiber of eta q is 0. Right, so this is something that we yeah, that's what being left exact equivalently means. Okay, so but now we take such a thing. So we have that this is T exact. It's because it's left F was left exact, so the stabilization is T exact. So G of the spectrum of this thing is this is simulated. Okay. And then we can consider the long exact sequence for Q to here. We want you to see that this right thing is zero truncated. You know the middle is zero truncated, so it's enough to check that this map here gives a mono on H naught. To check that eta q is a mono on H naught, or I mean pi naught, whatever you want to call it. Okay, so now we can also consider the right adjoint to F. And once again, d prime of F of Q is zero truncated. Once again, because F is lex. So if you take H naught of this map on the spectra, you recover the unit of recover the unit of this adjunction. Okay. Yeah. And then and so now it isn't too bad anymore. We need to check that this here is mono, but if we apply F to it, this is split by the co-unit of F of Q, and F is lex and conservative. So this thing is mono. Yeah. So it was a mono after applying F, but then because it's lex and conservative. Okay. Other questions about this? Good. Okay. So this now implies that. So to see where we are right now, we see that QCoh X CN C to tensor with C. So we've seen that this here, without the tensor product, is lex and conservative. So this is lex and conservative, which implies comonomic by our first lemma. Okay, so now we only need to do the stabilization, and this isn't too bad anymore. So if you have a colimit preserving functor between probably complete. Oh, we don't complete. All right. Between ordinary pre-stable categories. Then if F is lax and comonadic, then the stabilization of F is comonadic. Okay, so in particular, this implies that the stabilization of this thing is comonadic. How much time do I have?
9 more minutes.
Okay, yeah, I'm not going to make that, but then I'm not going to do the proof. But the proof is basically, let me paraphrase it in a few words. The point is that because it's lax, like you commute with taking connective covers, and then in Spectre you can somewhat take everything on connective covers. But after like taking connective cover, this stabilization of F just identifies with F. So this somehow tells you why you can import both the conservativity and having this this property of preserving the F split terms. Okay, and now we come to the end somehow, to the second part of the lemma. Okay. So now we have that this thing is comonadic. All right. And the second part is this Beck-Chevalier thing that people call Beck-Chevalier condition. I think it's just a different word for somehow adjointability. We need to check that this square is adjointable. We have the square is now the ends then. So you have this square, and this needs to be right adjointable, vertically right adjointable. Okay. And so the lemma that we, and this is once again somehow a very general lemma, which uses this adjointability that we've seen earlier. So the lemma is that if we start with a Cartesian square of, again, QCQS relative algebraic spaces. Sorry, no, this is wrong.
You mean QC geometric stacks with maps
Yes.
QC yeah.
No, I mean no. So it should be yeah. I mean I mean it's sort of no. I think you just need that the no. I think it's what I mean. Like I mean I think these maps should be QCQS relative algebraic spaces.
Yeah, that's right.
So I mean, these are some geometric stacks, but like I mean, it's a diagram of somehow relative.
Right.
Okay, then the if we apply spectrum of QCoh blank Cn, and then we tensor with our category C, this is this applied to the square. This is right at vertically, horizontally doesn't matter. Okay. Did I only have 9 minutes? Did you also account for the fact that we started later?
Yep. At the moment, it's like 2 more minutes.
Okay. Then I also want to do the proof of this, but it's quite funky. It reduces to the adjointability in the thing that we saw earlier via somehow using this category growth ST-conv and tensor conv. Okay. Right. So now let me prove theorem B. Sorry, prove theorem B. No, sorry. Proof of. First, we need to do the lemma. Okay, so we wanted to show that. This is an equivalence. Okay. Yes. But the point is, we can show this after applying spectra, as this thing is Lex, and it's Lex because it's a map into a limit of all of, and I mean all of the maps into the limit here are Lex. Okay. So now we can identify the spectrum of the totalization here. With the totalization of the spectrum. Okay, so we want to apply the theorem to, with the theorem, I mean the descent theorem that we had earlier, which is exactly what we've been working towards. So we want to apply this to.
Robin, I think there's a CN there, like connected, like QCoh
Yes.
UCN, right?
Thank you. I was waiting for the first time that I missed that because there's a lot of them. Oh, I missed another one. Okay, so we want to apply it to this thing, but we've just checked. We've checked the assumptions. So the first part was that the map from here to the first term, which is just this thing, is comodytic. And I mean, we've seen this effectively in like 3 lemmas. And the second part was this adjointability condition, which follows from this lemma. Yes. And this is the reason that I wanted to have spectra, because somehow this adjointability you get on QCoh, or only on the full QCoh. So yeah, that was why you need spectra here. Okay, so and now we are ready to prove the main theorem. Or I guess the other main theorem. Okay. So let us first. So maybe let me recall what we actually want to do, because it's been a long time. So to show. Multiplication map from QCoh x Cn tensor over QCoh y Cn maps to QCoh x times y Cn as an equivalence. And here x is QC geometric stack with delta x QCQS relative algebraic stacks. Yes. So this is what we want to show, and the idea was to somehow resolve x. So first. So if we assume that both x and y are affine, there's a confusion missing here. Then somehow the non-completed version is already an equivalence. And I mean, this is somehow just due to how these things are defined. I mean, this gives you modules, and this gives you modules, and then the tensor product gives you modules over the tensor product. Okay, so because it's already an equivalence before completing, of course, and so it's complete, so it's also an equivalence after complete. Okay, so now let us remove the assumption y. Yes. So only x is affine. Then we still know that quasi-coherent, the connected part of quasi-coherent sheaves is self-dual in modules over the connective over the connective spectrum in here. So this is basically due to the fact that if you somehow the dual of left modules will give you right modules. So if you have somehow just modules over something commutative, this is going to be self-dual. And maybe I should give a reference for this. This is HA4848. Very easy to remember. So in particular, tensoring with it preserves limits in Qoh with left exact transitions. This is due to the fact, I mean, as we saw at some point, that limits in this thing, if we take the forgetful functor, then limits with left exact transitions are exactly somehow preserved by this. So this gives you then a limit in PRL, and this is then by tensoring preserved. Okay. Thus, the source of this thing. Actually, okay, I guess it doesn't matter whether you take both complete or not. Yeah, but we don't need to complete because it's already going to be complete because it's F1. So, yes. So thus, the source preserves both coproducts and geometric realizations of faithfully flat of Chekhovs with faithfully flat maps U to X, U to Y in the Y. In the Y. Okay? Because certainly, if you take a coproduct and you apply QCoh CN, you will get a product which has left exact transition maps. And if you take such a thing, then because it's flat, you will again have left exact transition maps. Okay, so this thing is preserved. And then the point is that you can write any geometric stack as like a geometric realization of such a thing, where this is a coproduct of affines. Thus, without loss of general, can without loss of generality assume Y affine, and then we're good. Okay, so this was the part of the proof for X affine, and now let's do the general thing. And so far we haven't used the descent yet. All right. I didn't say. Sorry. I only said that the source preserves both these things.
Like you can similarly, like you can reduce to the fact of the target being affine. Okay.
I mean, the target obviously does, because the target is just quasi-coherent sheaves over something. So
okay, yeah.
certainly like transform these realizations to totalizations. So like on the target, you don't have to argue about anything. Okay, so So now, in general, let u to x be a faithfully, what's the word called? Faithfully flat map with u affine. And we assume that the statement of theorem B holds for x equals to un for all n. So we resolve with something where we already have the statement. And then we can consider this diagram that we get motivated earlier. Okay, I'm just putting completion somewhere now. Okay, and as I said earlier, this thing is an equivalence. Maybe for completeness sake, let me tell you what the maps are. So the thing is above is the thing that we care about, and this thing down here is the totalization of all of the separate ones. Then this down here is an equivalence by assumption on un, and this thing on the left here is an equivalence by the lemma. So the thing up there is an equivalence. So thus, the statement follows for x. And now somehow there's an inductive step that, so this is somehow some reduction step. And now we do this reduction step like 4 or 5 times, and then we're done. So we have the statement for x affine, which implies the statement for x with delta x affine, which implies the statement for x quasi affine, because these have affine diagonal. And then there's another statement which is SAG 3413. Is that this applies to sorry, no, I was too quick. So first of all, we get the statement for x with delta x quasi affine. And now the statement in SAG tells us that these relative algebraic spaces that I've been talking about the entire time have this property. So we get the statement for x an algebraic QCQS algebraic space. And then we get the statement for x with delta x relative QCQS relative. So you need to use this reduction step like 3 or 4 times to get there, but basically it's just some descent machinery to get to the case for x affine, and there it's some more or less explicit reason why this works. Yes, I think that's what I want to say. Thank you.
Yeah, let's thank our speaker. And then, yeah, like one thing, like in the square, like just nitpicking, the left bottom, like should be
yes.
Yeah.
There's too many CNs and heads in this talk, and
Yeah.
bound to one or two of them. Yes.
Yes.
So whenever there's a spectrum somewhere, it should be with connective, and almost all of the tensor products are complete.
Right. So yeah, let's thank our speaker again, and we'll move to the post-recording session now.